advanced power factor correction and harmonic mitigation. Good morning, everyone. Welcome to this technical deep dive into advanced power factor correction, or PFC, and harmonic mitigation. In today's highly electrified world, power quality is no longer a luxury, it's a critical requirement for efficiency, compliance, and reliability. Over the next few minutes, we will dissect the problems of poor power quality and explore the state-of-the-art converter topologies and filtering strategies being deployed today. Fundamentals of power quality. We start with the fundamentals, power factor. Simply put, power factor is the measure of how effectively electrical power is being converted into useful work. It is the ratio of real power, kW, to apparent power, kVA. A power factor far from unity, or 1.0, means you are drawing more current than you need, resulting in system inefficiencies. We have two key components of poor PF: displacement PF, which is the traditional phase shift caused by reactive loads like motors, and more critically today, distortion PF, which is caused by the non-sinusoidal waveforms, or dirty power, produced by modern electronics. The harmonic problem. Distortion is caused by harmonics. Harmonics are currents or voltages that are exact integer multiples of the fundamental frequency, so if your grid is 60 Hz, the fifth harmonic is 300 Hz. These are the direct result of nonlinear loads like variable frequency drives, LED lighting, and switched mode power supplies. These devices draw current in short, sharp bursts, distorting the smooth sine wave. The metric we use to quantify this distortion is total harmonic distortion, or THD, which is essentially the ratio of the RMS value of all harmonic content to the RMS value of the fundamental. High THD leads to costly problems, transformer derating, excessive heat on conductors, and tripping of protective relays. IEEE 519 to 2022 compliance. To manage these issues, we rely on standards like IEEE 519. This standard is crucial because it assigns the responsibility for power quality. The utility is primarily responsible for keeping voltage distortion, THDV, low, typically under 5% at the point of common coupling, PCC. The facility owner, however, is responsible for keeping their current distortion, TDD, within limits. The current limits are not fixed, they depend on the strength of the connection, quantified by the short circuit ratio, SCR. A facility on a weak grid, where the SCR is low, must maintain much tighter current limits, perhaps as low as 5%, to prevent that current distortion from causing excessive voltage distortion across the system impedance. Passive PFC techniques. Historically, and still commonly used for PFC, we have passive LC filters. These use inductors and capacitors tuned to resonate and absorb specific harmonic orders, such as the fifth and seventh. The advantages are simplicity, robustness, and low cost. However, they are fixed, meaning they can't adapt to changing load profiles. They are also bulky and, crucially, they introduce a risk of parallel resonance with the upstream system, potentially amplifying harmonics instead of suppressing them. Active PFC, the boost converter. The modern solution, particularly in electronics and IT systems, is active PFC, with the boost converter being the foundation. The key innovation here is the control loop. By rapidly switching a MOSFET or IGBT, the converter actively shapes the input current waveform. It ensures the current perfectly tracks the input voltage, making the load appear purely resistive to the source. This typically achieves a power factor above 0.99 and ATHD below 5%, making it compliant with most international standards. Advanced topology, interleaved boost. To handle higher power levels, say 1 kW and up, designers turn to advanced topologies like the interleaved boost PFC. This involves running 2 or more boost stages in parallel, but with their switching cycles phase shifted, often 180 degrees apart. The primary benefit is ripple current cancellation. When one stage ramps up, the other ramps down, dramatically reducing the input current ripple. This allows for smaller passive components, better thermal management, and significantly increases the power density of the overall solution. Bridgeless totem pole PFC. For maximum efficiency, especially in server power supplies and EV chargers, the industry is moving to the bridgeless totem pole PFC. The traditional diode bridge rectifier is the biggest source of conduction loss. The totem pole topology eliminates most of those high-loss diodes. It uses a fast leg of high-frequency switches, often made from wide bandgap materials like gallium nitride, GaN, or silicon carbide, SiC, alongside a slow leg of line frequency switches. By removing the diode losses, this design can achieve staggering efficiencies, often exceeding 98 or 99%. Active harmonic filters, AHF. While active PFC cleans up the input current for its own load, the active harmonic filter, or AHF, is a facility-wide solution. Think of it as a noise-cancelling headphone for your power system. The AHF connects in parallel with the nonlinear loads. It senses the total distorted current, calculates the exact harmonic content, and then injects an equal but opposite current back onto the line in real time. This dynamic injection cancels out the harmonics, leaving a clean sine wave for the utility. They are highly effective, dynamic, and can correct both leading and lagging power factors. Comparison of mitigation strategies. To summarize our options, here is a quick comparison table. Passive filters are cheap and reliable but offer limited, fixed harmonic reduction. Active PFC is integrated into the load and provides extremely clean power for that specific device, but it's not a global solution. The active harmonic filter, though the highest in cost, offers the most comprehensive, dynamic, and broadband harmonic cancellation, making it the preferred choice for industrial and commercial facilities facing complex, mixed harmonic issues. Benefits and ROI. The capital investment in power quality technology offers significant returns. By achieving a near unity power factor, you immediately realize cost savings by eliminating utility penalties and reducing capacity demands. Improving power quality means lower I superscript 2R losses, increasing energy efficiency. Crucially, it boosts equipment life by reducing stress and operating temperature on your transformers and motors, and increases system reliability by preventing unexpected downtime and equipment failure. Q&A and conclusion. Thank you for joining this deep dive into advanced power factor correction and harmonic mitigation. We have covered the fundamental problem, compliance requirements, and the latest topologies from passive filters to the high-efficiency totem pole designs and dynamic active harmonic filters. I hope this session has provided clarity on the crucial role these technologies play in a robust and efficient power system. I am now happy to open the floor for any technical questions you may have.